Hello, everyone. This is problem number 5 from the chapter 10 homework. And in this particular problem, we have a 0.1 molar solution of lysine, an amino acid, and that's all it says. So we need to figure out what lysine looks like in its fully protonated form. And when we examine the structure and then look at the total number of positive charges on it, and the number of protons, we see that the fully protonated form can be abbreviated H3A2+. So now we can make the pKa diagram. And our 3 pKa's are 1.77, 9.07, 10.82. Putting in then our structures beginning with the fully protonated H3A2+. We've got this. Okay, now we can think about lysine itself. And so lysine would be an electrically neutral form of the amino acid, and that is going to be right here. So this is what we have to begin with. And as a result, we know that we're starting like we were in problem 4 with an intermediate. So the step number A, or letter A, is to figure out the pH to begin with, and that's going to be halfway between the corresponding pKa values. And we have to be absolutely sure we use the right ones here. We're going to use these two to get our initial pH, from which we're going to get H+, and then begin the calculation. So the mistake that you could make is to use the wrong pKa's, for example, using the 1.77 and the 9.07. You'd absolutely not use that. You have to know to start with this one. Okay, pH is 1/2 of pKa2 plus pKa3. And when we get that value 9.92, 9.945, and we'll round this eventually at the very end when we report the value to 9.95. But for this part of the calculation, we need to not make any rounding errors. So we're going to keep that number when we get H+. And I get 1.14 times 10 to the minus 10th molar. And then step B is to make the assumption that is similar to what we did in problem 4. We're going to assume that the formal concentration of lysine, which is 0.1 molar, is equal to the actual final concentration of lysine, HA. And that allows us with the H+ concentration in HA to begin doing some calculations. All right, in this particular problem, we have 3 reactions. We're going to number 1, 2, and 3, the 3 dissociations, beginning with the most protonated species. That's going to be described by Ka1, whose value is 1.7 times 10 to the minus 2. And then we've got our second dissociation reaction. Mathematically described by Ka2. And then the third one. And we'll keep referring back to these as we work through the rest of the problem. So those are those 3 values. And we're going to go on to the next page, beginning with the Ka expression for part 1, for reaction 1, and then the Ka expression for reaction 2 and reaction 3, to give us the concentrations of the species that are 1 and 2 protons removed from our lysine, which is this one. So next page, we'll begin with that second reaction. So in the second reaction, we've got H2A plus dissociating, and we end up with the second Ka's expression, looking like this. That's going to give us a value for H2A plus. And that value is going to end up being 0.0133 molar. And so when we get the value from that, we'll probably round that at the very end. And we'll go then to the first dissociation reaction. And if we look back at that, we see that once we know the concentration of H2A plus, we can simply plug it in along with H plus and find H3A 2 plus. So we're going to get that from Ka1. And that expression looks like this. So a little rearranging and then plugging in of the numbers we know. Like I said, we know H plus from the previous page. We now know H2A plus from the previous calculation. And we know the value for Ka1. And then that can give us the value for H3A2 plus. And there I get 8.9 times 10 to the minus 11th molar. Okay, finally then, if we go back to the third reaction, in the third reaction, remember that we know the assumed concentration of HA. That's our formal concentration. We know H plus again, and we know the value for Ka3. We should be able to calculate A minus from the equilibrium expression. So from number 3, once again, we know H plus. We know the value for HA, that's going to be 0.1. We know the Ka3, and that's going to give us a value for A minus. And that value that I get is 0.0132. You'll always find that the two species that are on either side of the intermediate, in this case, our intermediate is HA. So the species that are one proton on either side are going to be A minus and H2A plus. Those concentrations will often be very similar, and you should expect that. Later, when we actually report our final results, we're going to round these to 2 significant figures. But for now, when I did the calculation on my calculator, I didn't do any rounding, and I used these numbers unrounded to then do the final step, which is the correcting of the assumption that we made at the very beginning. So we assumed that the formal concentration of 0.1 molar was equal to the concentration of HA. But in fact, we can see that a significant amount actually of the formal concentration is in the form of the fully deprotonated stuff and then the diprotic intermediate. So let's correct our assumption by taking all of the concentrations of all 3 of the forms that are not HA and subtract them from the formal concentration, and we'll get the HA concentration. So the actual concentration of HA should be, well, let me just redo that. That didn't look very good. So the actual concentration of HA is going to be 0.1 minus 0.0133 minus 8.9 times 10 to the minus 11th minus 0.0132. And so corrected, that HA concentration ends up being, again, using the unrounded values, 0.073 molar. And if you make some rounding mistakes in there, you might get a number like 0.074 or something like that. Okay, so now we have the corrected value for HA, and we can then summarize all of the rest of the concentrations as well. From the previous page, we found that pH was 9.95. And what we found was the concentration of H2A plus 0.013 when it's rounded, concentration of H3A 2 plus was 8.9 times 10 to the minus 11th molar. And then finally, our concentration of A minus was 0.013 molar.